Today, I wanted to talk about multi-user systems, in particular about the interference channel, where waterfilling plays a role. But then I thought that I could talk about other different aspects of waterfillings. So this is going to be actually the talk. It's going to be like a trip, a journey around different aspects of waterfilling, and at the end I will talk about the interference channel. Okay? So, okay, do you have a pointer?
No.
I think I do have one. No, I think I do have one. Yep. So, this is the outline. Actually, I will spend like half of the time talking about different aspects of waterfillings. Oops. And the other half of the talk talking about waterfillings for the interference channel. And the pointer is not going to last, but it's okay. So I will start talking about the classical waterfilling, which is something we all know, but it's good as a starting point. Then I will talk about where we can find waterfillings, other kinds of waterfillings in this life. And then I will give a result which will be very important for later for the interference channel. This result is a new geometric interpretation of the waterfilling. You will see what it is later. Okay? So I will start with single-user systems and then multi-user. The role of waterfilling in single-user and multi-user systems. These are my collaborators on different topics related to waterfilling. So it goes back to my PhD dissertation, and it comes to some collaborators from Rome in Italy. Okay, let me start with the classical waterfilling, something we all know. If we have a channel with Gaussian noise, we know that to maximize mutual information, we need to transmit with a Gaussian code. And then the mutual information is given by log of 1 plus the SNR, right? Now, if we have a set of parallel and independent channels, what happens is that the total mutual information is given by the sum of all these logs. Great.
Undefined if you want.
Okay, that's okay. So if we have a set of parallel channels, we have the sum of the logs of 1 plus SNR, right? And the SNR is given by the gain of the channel and the power that you allocate. The problem is precisely how to allocate the power over these parallel channels. Okay? This can be formulated like this problem. Maximization of this subject to a total power constraint. Well, if you solve this problem, which is very easy to solve because it's a convex problem, the objective is concave, the constraints are linear, this is the solution that you get. Right? And this is the waterfilling that we all know. Right? By the way, this goes back to Shannon, like everything. Okay? So this is the classical waterfilling. I call it classical, you will see later why. Otherwise, this is known as waterfilling only. So, why is it called waterfilling? And what is this mu? Okay, I'm sure we all know this. The idea is that it has this graphical interpretation. So you can plot the inverse of the channel gains, and then it turns out that if this difference between mu and the inverse of the channel gain is positive, then the difference is the power that you need to allocate. So it's this, the power. And if this difference is negative, this operator here sets it to 0, which is the case in these two channels. So you can interpret this as having water here with some water level, which is mu. So mu is the water level. Depending on mu, you will use more or less power. In fact, the area of this is the total power. Okay? So in particular, typically you don't have the mu. You have a total power, and you need to find the mu that achieves that total power. Okay? So this is why it's called waterfilling, because it has the interpretation of pouring water. Now, can we find other waterfillings in life? Well, actually, yes. For example, this is one. I call it gap approximation waterfilling. This happens when you have also a set of parallel channels, but in this case, you don't want to use a Gaussian code. You want to use some practical constellation like quantum constellations, and you don't want to take an information theoretic approach. You fix the error probability, and then you want to find the relationship between the number of bits that you can transmit with that error probability and the SNR. It turns out that approximately this is the relation, log of 1 plus SNR divided by some gamma. So it looks like the previous log of 1 plus SNR. But this is completely different. This is not information theory. Anyway, once we have this, we can solve the same problem as before, and we get a very similar water filling with the gamma. But this is completely different, actually. This is...
The gamma is just to accommodate some kind of Gaussian versus QAM.
Exactly. It's a penalty that you pay for not using Gaussian coding, for using QAM. So it's a number larger than 1. Okay, so this is another example of water filling. Do we have more examples? Yes, this is a more recent one, mercury water filling. The idea is similar. The setup is similar. You have a set of parallel channels. You want to use constellations, practical constellations, but here you still take an information theoretic approach. So with those constellations, you want to maximize the mutual information. Well, if you do that, then you get some kind of water filling, but it's a bit different. The interpretation is this. The interpretation is that still you plot numbers of the gains, but now instead of pouring water, first you pour mercury. Okay? So you put mercury on each channel, you put a different amount of mercury, and then you pour the water. It's another type of water filling. Okay. Recent one. This is another one. It's a classical one also. It goes back to 76, so it's quite old. I call this MMSE water filling, minimum mean square error water filling. The idea is similar. We have a set of parallel channels. We don't take an information theoretic approach. We want to minimize the sum of the mean square errors. Mean square error of the estimation at the receiver, the estimation of the transmitted symbol. It's a different setup. It's a signal processing approach. So this is the problem formulation, and if you solve this problem, which is convex, so you can solve it globally, you get this kind of water filling. It's a bit different. Here, instead of having the water level on this side, we have the water level times also the channel gain with a different exponent, right? So it's similar but different. It's still a kind of water filling, right?
Is this a kind of, is there a multi-dimensional signal including orthogonal channels here?
Oh, yeah. These are orthogonal channels, orthogonal parallel channels. Yeah, all these examples are orthogonal parallel channels. Yeah.
So the other ones I understood, but this one
The same thing. Here you don't really need to talk about constellations. You just minimize the mean square error between the transmitted symbol and the estimated one. You don't need to explicitly talk about constellation. So it's a different approach. Are there more water fillings out there? Yes. For example, this is another one. You want to minimize the maximum of the mean square errors in a minimum multi-carrier system. If you formulate the problem and solve the problem, you get something like this, which looks like the previous one, right? It has the same shape. The difference here is that this is multi-carrier, so on each carrier, we have a different water level. K is the index for carrier. So this is like a water filling, but with multiple water levels. But still, it has the flavor of water filling. Okay? And before we always have to find the water level to satisfy the power constraint with equality. Right? Here it's more complicated. Here we need to find all these water levels to satisfy the power constraint with equality and also these strange constraints. So this is a more complicated water filling. Are there other water fillings? Yeah, many. So if we minimize the power with equal mean square errors, that's a different problem setup, you get a water filling. If you want to minimize an approximation of the average bit error rate in parallel channels, you get a kind of water filling. If you want to maximize the harmonic SINR, you get another kind of water filling. If you want to minimize the average bit error rate, another kind of water filling. And rumor has it that other water fillings are coming. Okay, I know actually more than one water fillings coming. And there are other water fillings out there, which I missed. But anyway, the idea is that we are surrounded by water fillings. So it's good to understand them. So, by the way, I'm calling all these things water filling. But is it okay or not? I mean, are we entitled to call these things water filling? Because the classical one had the interpretation, right, of pouring water. But what about these other water fillings? Well, the answer is that yes, you can always find a nice interpretation of pouring water. For example, consider this water filling, which is quite general. Here you have some numbers. This could be the inverse of the channel gains, like before. But here you also have some numbers. This could be the inverse of the channels with the square root, whatever you want. Does this have a water filling interpretation? Yes, but you need to go to 3 dimensions. So if you go to 3 dimensions, after a change of notation here, you can actually give each channel a width. And once you do that, it's a fixed width. Once you do that, you can pour the water. Okay, so it has the water pouring interpretation with the water level.
Do you think you can argue that you can call things with multiple Lagrange multipliers?
Yeah,
I mean, sort of, I would say, oh, it's water filling if you have one Lagrange multiplier that defines the top of the...
Okay, the truth is that I haven't tried to find a graphical interpretation, but I bet you that you can find one. Probably each carrier will have a different... It will be like also 3-dimensional. Each carrier will have a different offset or something like that. So, yeah, I'm sure.
Now his point is the water filling comes about because there's one Lagrange multiplier and that corresponds to the water level.
Uh-huh.
But now isn't that what you're saying?
Yeah,
That
that's
there are
sort of
multiple.
what I would say makes it water filling.
Right. Here you have more constraints, so your KKT has more.
For example, I'm just making things up.
Okay.
You could use different liquids with different densities on each carrier,
Yeah.
and then that will probably give you different levels. I don't know. I'm sure you can find some interpretations, or you can introduce a different offset on each carrier, so to adjust the levels.
Yeah.
I'm sure you can find a nice graphical interpretation. Anyway, so what's cool about these water fillings expressions anyway? I mean, why are they so popular? There are several reasons. One of them is that they are simple and nice closed form expressions, which we like closed expressions, right? Rather than numerical results only, we like closed form expressions. So this is a nice one. It has an appealing graphical interpretation. Okay, we've been discussing about that. Another important aspect is that if we want to evaluate this numerically, it's very easy to do that in practice.
I think some students would disagree with you.
No, come
God,
on.
Danny.
No, what?
It's intense iterative process.
Like
No.
You get this formula, but then you go, well, what is the right mu? For
Exactly. Okay, so you need to find the right mu. Once you have the mu, that's it. How do you find the right mu? The popular way to do it is using a bisection method. So you choose a large mu that exceeds the power and a very small one which doesn't achieve the power, and then you start doing bisection, right? And in a few iterations, you get very close to the right mu. That's what everybody does. That's okay. But there is another way to do it, which I kind of like, which is, I call it hypothesis testing. The idea is that instead of finding this mu as you go to infinity, here you try to find the right hypothesis. By hypothesis, I mean some channels will be active and some channels will be inactive, on and off. So you try to find the right hypothesis, what channels will be active and what channels will be inactive. If you can do that, then you can find the exact mu in one shot. So actually you can do that. You may think that how many hypotheses do you have? 2 to the n, right? No. If you look at the structure, you can always sort out things, and at the end you have n hypotheses. So it's linear. It's very nice. But I will argue even more. In the case of multiple water levels, how do you do bisection with multiple water levels and with many constraints there? I don't know. But if you do hypothesis testing, you can still do it nicely.
So what is hypothesis? So you're saying whether it's either you pour in there or you don't pour in there? That is the
Well, the interpretation is that
carrier.
that you pour, but the question is how do you find these water levels? So this is a way to find the exact water levels. And yeah, anyway,
Okay.
there is this paper where we talk about that. Anyway, the point is that this expression is very nice in many ways, but my point is that for some applications, in particular for the interference channel that we will talk later, this is not good enough. This is not enough to prove convergence of some iterative algorithms. And then we need something else. So we are going to see an alternative expression of waterfilling. Okay? So let's go for it. This is the waterfilling expression. I have changed the notation a little bit. Typically here we have the inverse of the channel gain. So you can think of that as the inverse of the SINR, which I call INSR. Interference plus noise to signal ratio. Okay, you can think of this as the inverse of the channel gain if you want. Anyway, so we want to solve this subject to this constraint. Right? Okay, now if you look at this, what is this? Why am I writing this, by the way? This is like a more general waterfilling. The waterfilling, what it does is, if the number is positive, it leaves it like that, and if it's negative, it makes it 0, right? So it's a clipping from below. We can generalize that. We can say, okay, clipping from below, 0, and clipping from above. Why is that useful? Because sometimes you have mask constraints. You don't want individual powers to be larger than some value. So this is a two-way clipping. Okay. Anyway, that is not a big deal. So if you look at this is actually a projection. You project one number onto that interval, right? It's a projection. However, this is not a projection because this is a projection if you know the mu. But we don't know the mu yet. So this is not really a projection because we need to find the mu. Okay? If somebody gives you the mu, yes, it's a projection, but otherwise it's not. And what's the problem with that? Well, we will see later that for showing convergence of some algorithms, we would like to express the waterfilling as a projection without water levels. It looks weird, right? But actually, we can do it. So let's see how we do that. Let me first start with this very simple result. Okay? Let me define this set. This is a simplex. A simplex is the set of points that are non-negative and that they sum up to some value. This is a simplex. The only difference is that I include an upper bound here, but forget about that. Consider only the non-negative constraint and the summation equal to some value. This is a simplex, right? Now, I want to project one point, x sub 0, onto this simplex. By definition, the projection of a point onto a set can be written like this. Can be written as finding a point x that has minimum distance to the point, but that satisfies the constraints. That's the projection. Okay? The solution to this problem will be the projection of x sub 0 onto this set. Well, this is a convex problem. It's very simple. You form the Lagrangian, KKT conditions, and you find the solution. And it's given by this. No big deal. But look at this. It looks like the waterfilling, right? It's like the waterfilling, actually. The difference is that we have a plus sign here. Before we had a minus. But actually, it doesn't make any difference. If we choose this point, x sub 0, to be equal to minus the INSR, it's the same thing. So here comes the final result. This waterfilling, the classical expression of the waterfilling, can be also written like this projection. The projection of the vector of the inverse gains onto this set. This denotes projection. Projection onto this set. And this is the simplex. So it's like magic. It's very simple. It's magic. But so here we don't have any waterfilling. So we finally have the waterfilling as a projection with without water levels. Sorry, I meant without water levels. And this may look like a curiosity to you, but later this will be important. Any question about this? I think this is it's good to know.
This also will work for multiple constraints. So you're looking at one constraint, and your simplex is a one power. All the power has.
Yeah, the sum of the power has to be equal to that, and then you have upper and lower bounds. Yeah.
Is that always the unified constraint in all waterfilling problems? That's it, right? There's only power. Are there any additional constraints?
Well, some strange waterfillings have other constraints. So in that case, you have to take care if this holds or not. This holds for the power constraint. Okay. Anyway, so this is a useful result to keep in mind. You never know when it can come useful. And this is the graphical interpretation. Consider 2 dimensions, so a vector of power with 2 dimensions, P1 and P2. So this is the simplex, this line. This line is the simplex, right? So just take one point, for example, this one, of inverse gains, and just let's do this. We take the minus that point. Minus means that we go here and here, minus, and then we project minus the point, we project that. Projection means essentially the perpendicular line. Here we have. Anyway, so this is the power that we get. If you choose this point, something strange happens. You take minus the point and you project. Here you cannot use the perpendicular line because you will be going outside. So you need to bend a little bit. Which means that one power will be 0 here. But this is not really important. It's nice to have a graphical interpretation. So the points inside correspond to points with positive powers, all of them. Points outside have one of the powers 0. But that's not a big deal. Anyway, so let's summarize for the moment. We have seen
inside and outside, it's the shaded area.
Yeah,
inside.
shaded means that
All
when you
powers
project,
have been done 0.
yeah, exactly. So this is a very different graphical interpretation from the pouring water, right? Both can be useful. So let's see what we have seen. We've seen an expression for the classical water filling and the graphical interpretation. Then we've seen many expressions for different water fillings, and also graphical, more general graphical interpretations in 3 dimensions, maybe higher dimensions in some cases. And we have introduced this new expression of the water filling as a projection, which will be important later. Okay? This is all I wanted to say about water fillings in single user systems. Now we can move on to the role of water filling in multi-user systems. This is a good moment to ask questions about what we have seen, if you want. If not, I will start with the multi-user case. Let's start with the multiple access channel. Okay, this is just to warm up. Okay, this is not the main part of the talk. So multiple access channel, we have several users transmitting to a base station, and we consider a vector signal model. Okay, MIMO channels. This is a signal model. Anyway, this we consider Gaussian noise, by the way. So the capacity region of the Gaussian multiple access channel is well known. Okay, it has been characterized. The only problem is that as you increase the number of users, the dimension of this region increases. So it's sometimes difficult to deal with that. So it's sometimes useful to use one parameter only. Typically, it's the sum capacity. Sum capacity is useful. It's one parameter regardless of the number of users. And the sum capacity happens to be the maximum sum rate under the power constraints, which is given by this problem. Okay? This is the sum rate of this multiple access channel. I don't want to go into the details, so don't worry about this. The idea is that this is the sum rate. The sum capacity is the maximization of this with respect to queues. These queues are the covariance matrix of each of the users. So each user has an independent power constraint. So this is the problem. Again, this is a nice problem. It's convex. The log det is a concave function. This is linear, and this is cone constraint. So everything is convex here. We can use an interior point method to solve this convex problem, and that's fine. We could stop here. However, some people propose a very nice algorithm to compute this. Very nice. I'm sure some of you know this because it's very popular, actually. This nice approach was proposed in 2001. The idea is to optimize each variable at one time. So you optimize with respect to one user, then with respect to the second, third, fourth. But if you do that, is this going to converge? If we optimize at each time with respect to only one user, do you think that will converge to the global maximum of this problem? Well, it happens that yes, because this this iterative maximization is a particular case of a general approach called Gauss-Seidel. And this is a standard in textbooks. So there are results that say that if you have a problem that is jointly convex, you can use Gauss-Seidel and it will converge to the global optimum. So you don't need to prove anything. Essentially, this is well known. So you don't need to prove anything, and so it converges to the global optimum. Why do we want to optimize in such a sequential way? Because everything becomes very simple. This is what I'm saying. Convergence to a stationary point is guaranteed. So why do we want to do this iterative maximization? Because when we optimize with respect to one user only, the problem is something like this, and the solution is well known. This is a well-known solution. We know the solution in closed form. So each iteration of this iterative process is a one-shot solution. It's very nice. And the solution is given by this. I don't want to go into the details, but the idea is the eigenvectors are given by the eigenvectors of this. And here we have the power allocation. And this is where I want to get at. This power allocation is a Waterfilling. So when we optimize one user, what happens is that user will be Waterfilling the interference or the channel, if you want, the inverse of the channel that the user sees. Okay? So one optimization, one iteration is Waterfilling. So the idea is that you do one Waterfilling for one user, then for the second, iterative Waterfilling. This is called iterative Waterfilling algorithm.
So for each user, you actually assume that the other user's powers are fixed, right? That's
Yeah.
That's why
Yeah.
it makes it easier to
Yeah. So this is.
Do you come back to the first user? I mean, how does? So obviously, one has to read to figure out how to make
Yeah. So essentially, when you optimize with respect to the kth user, you consider the other ones fixed.
Right.
So this gives you like an equivalent noise plus interference covariance matrix. So you optimize that user. But then, even if the other users were optimum before, now they will not be because you have optimized the user k. So they need to be. So it's a never-ending process. So you have to do it. Although the convergence is like in 2 iterations, so it's really fast. So it's nice. Anyway, this is the multiple access channel, broadcast channel. What happens with the broadcast channel? Well, Gaussian broadcast channel is more difficult, but recently some smart people show that there is a duality between broadcast channel and multiple access channel. So at the end, if you want to compute the sum capacity of the broadcast channel, you can actually compute the sum capacity of the multiple access channel. The only difference is that now instead of having one power constraint for each user, you have a global power constraint. This makes sense because here you have one transmitter and several receivers, right? Broadcast. So this one transmitter will have one global power constraint. That's why you have this. Anyway, so this looks similar, but you cannot use Gauss-Seidel here. You cannot do an iterative Waterfilling because this constraint is coupling all the users. So you cannot do the nice iterative Waterfilling here. However, people do things, and actually there are many things you can do here. One common approach is to use a dual decomposition approach. And the idea is that you relax this constraint, you form the Lagrangian and you relax this constraint. And if you do that, then you can use a variation of the iterative Waterfilling. I will not go into details, but the idea is that still, at each iteration, what you do is you fix the water level, you do the Waterfilling for all the users many times until this converges. Once this has converged, you update the water level. There is like a master problem updating the water level. So it's different than the algorithm before. But again, iterative Waterfilling is still there. So everywhere where you look at, you have a Waterfilling. Anyway, this was to warm up. Let's talk about the interference channel now. Any questions so far? Let's see if we can find Waterfillings in the interference channel. Well, yes, actually we will see different variations. Sequential, simultaneous, asynchronous, we will see many things. The problem with the interference channel is that we don't really know the capacity region, so we cannot attempt to obtain any fundamental limit. So what we will do is a very common approach is to consider a suboptimal scheme. What do I mean by that? Well, each user will treat the other users as Gaussian interference. instead of trying to do some multi-user detection, each user will treat the others as Gaussian interference. So this gives us an achievable region. Okay, this is a common assumption done. Additionally, we want to obtain, in these interference channels, like ad hoc channels, we want to obtain distributed algorithms. So we don't want some centralized computation or anything. We want something distributed. Okay, so a natural framework for this, and this is not new, I mean, some other people have done that, is game theory. Okay, it's to model this network as a game. And this is very different from the previous multi-user cases. In the broadcast channel and multiple access channel, there was only one objective, right? There was only one objective, which was this death of all these things. One objective. Here is very different. Here we take a game theoretic approach, and then each user will have a different objective. So it's very different. We don't talk about classical optimization anymore. We talk about game theory. It's a very different setup. Okay. So by the way, this initially was proposed in the context of DSL in 2002 by Wei Yu, George Ginis, and John Chaffee. Okay. So the idea. What is the idea? The idea is that we have several users, several links. So one thing we can do is, by the way, yeah, I forgot to mention something. We will say more details about that. But in game theory, what is the optimum of a game? In a classical optimization, the optimum is the optimum. Is what the point that achieves the maximum or the minimum, right? But in game theory, what is the optimum? So, well, in game theory, we have what is called Nash equilibrium. That's a point where each user is happy. So it's not really the optimum, the global optimum, because there is no notion of global optimality in the game. But it's like an equilibrium point. So we are interested in Nash equilibrium points from this game theoretic perspective. So the problem is, well, these equilibrium points are nice, but how does the system evolve to this nice equilibrium point? Well, we can say, okay, let's try to do some kind of iterative waterfilling. This is what they did in 2002. So what they did is that at each time, one user or one link does a waterfilling, and you do this for other users sequentially. It's like in the multiple access channel case. But here is a different setup. This is interference channel. It's very nice because it's distributed. Each user only needs to measure the interference and then do a waterfilling on that interference. So it's completely distributed. Each user doesn't need to know the channels from the other users or the power constraints from the other users. Nothing. It's completely distributed. It has a very simple implementation. At each iteration, one user does waterfilling. That's it. So very simple. And it has a nice interpretation, of course. Drawbacks. Well, of course, if you have a sequential update in a, let's say, ad hoc network, this means that you need some kind of synchronism, right? You need some kind of scheduling. Who is going to update at what time? That's not nice. Then, because of the sequential update, if you have many users, what happens is that convergence will be slow because the users will be waiting most of the time for their turn, right? So that's not nice. And, well, how can we deal?
Can you sort of remind us what the physical situation is? So, like in the Eugenics Chaffee work, right? There's an OFDM channel, like a multi-carrier channel.
Okay.
Shared.
Yeah.
And there's users, and each one has a receiver. So the result is it's multi-carrier interference.
Exactly. Yeah.
And
So
in your situation that you want to work on, is it MIMO antenna?
okay, let me rephrase it in the wireless case, but it's the same thing. In the wireless case, you can think of not MIMO. You can think of single antennas, and then you can think of having an ad hoc network with many links. So you have many pairs of transmitter and receiver, and then each link wants to transmit from the transmitter to the receiver.
So one dimensional? I mean, each link.
Oh, multi-carrier, yeah, multi-carrier, yeah.
They can do
Yeah, it's multi-carrier. Yeah, because if it's only one carrier, then each user will use the maximum power. And yeah, exactly. No, that's a good point. So here it's multi-carrier, and what we want to optimize actually is the power allocation on the.
So it's one transmit antenna, one
exactly.
and then multi-carrier.
Exactly. Yeah. It's one antenna and multi-carrier. Yeah.
But then you're assuming something about the network as well. So is the interference model somewhat information theory that all the transmitters just transmit in their own time, independently? They're all transmitting simultaneously, meaning? Yeah.
Everybody's transmitting at the same time, so each user sees the interference from the other ones, and we assume that somehow the user can measure the interference, the level of the interference, so he can do waterfilling. Okay, so these are the drawbacks, right? You need synchronism, and convergence can be slow. An obvious way to deal with that is, instead of doing a sequential update, you can do a simultaneous update, right? By the way, proving convergence of these, in the other case, we could just say, okay, it's Gauss-Seidel, it's going to converge, because the problem is jointly convex. Here, it's different. This is game theory. We don't have one problem formulation, one objective. So convergence is not guaranteed. You have to prove it by hand. That's what they did in 2002. You have to prove it by hand, and you need to find the conditions under which it converges. Okay. Now we propose the simultaneous. Okay. Whether this is going to converge is another issue, but we can propose whatever we want, right? Anyway, clearly, if this converges, it will converge more or less independently of the number of users, because you don't have to wait for the other ones to update. You can do it at each iteration. So clearly, we solve that problem. The question is, will it really converge or not? So we are going to give conditions under which it converges indeed. Okay. So this, what we are going to see now is conditions under which the sequential converges, conditions under which the simultaneous converges. By the way, here something additional that we consider is we consider spectral mass constraints. Okay, previous work didn't consider spectral mass constraints, but of course in practice they are important. But since we are going to take a projection point of view, including spectral masks or not, it's really not an issue, because for us it's going to be a projection anyway. So if you remember the previous interpretation of the waterfilling as a projection, having a maximum power constraint is just a projection. So
to me it's not so clear that the simultaneous
yeah, I know.
Because
also
like some people, if you do parallel updates, right, they'll say, well, if you could go one by one and include the last person's improvement before the next person operates, right? Gauss-Seidel is better than for instance, a parallel is like a Jacobi.
Yeah, for sure. It's not obvious. You need to prove that. Yeah. But if you imagine that you have 1,000 users. If you do a sequential update, you will have to wait 1,000 units of time before you can do your own update. So, whereas if it's simultaneous, after 1,000 unit of times, all the users will be.
Do a lot more computation. It depends on how if you say, oh, it's time, and I can in 1 unit of time do one person, or I can do n people. But if you're counting the effort in terms of
we can't.
Computation you do.
The definition of iteration is very important indeed. We consider time like real time, because it's more computational work, but it's done in parallel by different links. But if you define the iteration differently, it's a different situation. Okay, this is the idea. Let me give you the signal model quickly. So we were talking about one antenna, so it's a scalar channel, but multi-carrier. Okay, and we want to maximize the mutual information. So it's the sum over the carriers of the log of 1 SINRs. Okay, here in the SINR we have the power that the user is using. This is the channel gain, And here we have the normalized noise and the interference. This is the interference from the other users. Okay, this is important. This is where the suboptimality comes from treating the other users as noise. Okay? But anyway, this is a common signal model. So each user wants to maximize his own rate.
What is that SNRQ on the right hand?
Yeah, it's just some definitions. I don't really want.
Factors.
Yeah, scaling factors. Yeah, for convenience. But yeah, let's not get into that. Okay, what are the constraints? Well, each user has a power constraint, and then spectral masks. Okay. And as I said before, this setup was considered in 2002 already. Okay, so this is the formal definition of a game. We define a game as a set of Q users. Each of them has a feasible set, the constraints, and each of them has an objective function, the rate that we saw before. Okay, this is the game. So let me talk about Nash equilibrium a little bit. I said before that a Nash equilibrium is a point where each user is happy. Okay, so if you fix the other users, one user will be happy only if he waterfills the other ones, right? So if I'm saying that, if I'm talking about one point where all the users are happy, it means that all the users are simultaneously waterfilling the other ones. So it's like a joint simultaneous waterfilling. So this is what I'm writing here. A Nash equilibrium has to be a point where all the users simultaneously waterfill the other ones. So something like this. Okay? Okay. It's very easy to show existence of Nash equilibrium. Uniqueness is more difficult. But anyway, here we care about how the system evolves into that Nash equilibrium. Okay? So we care about the algorithms. Well, it's good to know that a Nash equilibrium exists. If it doesn't exist, we cannot prove convergence of any algorithm, right? So it exists. Let's see the convergence. So this is what they did in 2002. They had to prove convergence. Let me say that again because it's not obvious. And this is the idea of the algorithm. So for some number of iterations until convergence, we update all the users one by one. How do we do that? Well, at iteration n, the user Q updates himself by waterfilling. This is a waterfilling operator. By waterfilling on the interference generated by the other ones. Since it's sequential, the power from the previous users up to Q minus 1, we take the updated power already, n plus 1. But the other users have not been updated already, so it's from the previous iteration. Well, it's sequential. So, does it converge or not? Well, these are the conditions for convergence that were found in 2002. Okay, so if this is true, it will converge. Okay, essentially, yeah, Q is the index for the users. So this is the direct channel from transmitter Q to receiver Q, and this is the cross channel from transmitter R to receiver Q. So what we can see here is that if the direct channel is very large compared to the cross channels, this will be very small, which is good. It makes sense, right? It's like if you have the links, if the links are separated from each other, they will not interfere a lot, and everything will converge. The problem with this condition is that in practice this is like never satisfied, because here you want this condition to be satisfied for all the carriers. K is the carrier. So just think, if you have a network with many users, if only one user has a deep fading in one carrier, the channel gain for that carrier will be very small. This will be large and this will not be satisfied. So it doesn't make sense, right? Only because of one user has a deep fading in one carrier, you cannot guarantee convergence. Doesn't make sense. So here we have a more relaxed condition for convergence, where it's very intuitive. We only need to take into account the good channels. So you don't need to take into account those channels in fading. It's very intuitive, but you can do it. So it works. I mean, if you can show this other condition, which is very similar, but you get rid of the bad channels, and also you take the average here, which is also more relaxed, then you can guarantee convergence. Some other people have been improving this condition, by the way, okay? I'm just giving you the original one and the one we obtained, but other people obtain different improvements. Okay?
So what is R?
Or is somebody
Yeah, this is the index of one user. This is the cross channel between transmitter R and receiver Q. So it's the cross channel.
So in the bottom is the loop theorem.
This is the same thing. Yeah, the same thing. Yeah, but here you only consider the carriers that are not invading. So precisely what makes this condition bad is fixed. So which is the carriers invading. And I want to show you now some numerical results, and you will see the difference. It's the difference. By the way, so this is for one particular realization of the channel, right? So this condition is either satisfied or not, right? So what we want to compute in practice is how often this is satisfied. So in the simulations, I will show the probability that it's satisfied, actually, assuming generating random channels. Let me talk about the simultaneous first. The simultaneous is the same thing, but at each iteration, each user, all the users are updated using the interference generated in the previous iteration from the other users. Okay? So it's simultaneous. The truth is that when we started with this idea, we saw that it converged in practice, but we didn't really know whether we could prove convergence, because after all, it's simultaneous, so it's not clear.
So, let me try to understand this Waterfilling operator a little bit, right? So, for a particular user, what is it that user needs to know about everybody else?
Okay. The only thing the user needs to know is the global interference. So the sum of the power of one user times the channel gain, the sum over all the users.
So the received power essentially
from all the users, the interference level. So this is the way I write it here. So the power from the different users generate an interference through the cross channels, but really in practice the only thing the user needs to know is the measured interference. That's it. So it's local. Okay, so the thing is that we worked on this for a while. We couldn't prove it, and the key to prove this was the interpretation of the Waterfilling as a projection. What we saw before, this was the key, and I will say more about that. Anyway, this is the condition for convergence. Don't look at this because it's difficult to interpret. Look at this one. Okay? This is a corollary. I don't know if it looks familiar, but this is exactly the one we saw before for the sequential. So it's actually pretty surprising that the same condition that guarantees convergence of the sequential also guarantees convergence of the simultaneous. I think it's nice. Let me show you some numerical results so that you can see. Here I'm plotting the probability that the conditions are satisfied. Of course, we would like the probability to be 1. Right? And I'm plotting the probability with respect to this parameter. This parameter is the distance. This is like the distance between different links divided by the distance between transmitter and receiver of the same link. So in a way, this quantity is telling how separated the links within the network are. So of course, if this distance is large, it means that all the links are separated. Of course, everything is going to converge, right? So probability will go to 1. Which is what we see. As this increases, the probability of all the conditions go to 1. But of course, in a real network, we have links together. So we need convergence when they are together also. So as this decreases, the probability goes to 0, right? So this is the original condition in 2002. So like in this region, the probability that is satisfied is not very large. This is an improvement obtained by Luo and Pang in 2006. It improves a lot, right? And this is our condition, the black one, which improves a lot. And hopefully somebody else will improve even more this condition.
So what is the...
Go ahead, you ask a question and I'll ask.
So what is the channel model here?
Oh yeah, the channel model is each channel is generated randomly from a Gaussian distribution normalized to variance 1.
And what is this parameter D?
D is like,
Context of that channel? Yeah.
this is like, I said that the variance of the channel is 1,
Yeah.
so you can scale the variance according to the distance. So what we did is we explicitly put this distance, this scaling here in the distance. So we generate all the channels with variance 1, and then we include the distance explicitly. This way we can plot these plots.
So the distance is somehow, it effectively makes all of the interferers, like if you're at some normalized distance, all the interferers are at some other distance d from your receiver.
So yeah, if you choose this distance large, it means that if you choose the distance large, it means that they are like far away. Yeah.
So all of the work was, it's always the same algorithm. It's an iterative water.
Yeah, the same algorithm.
Multi-carrier.
Same algorithm.
What you have is 3 generations of successively weaker sufficient.
Exactly.
And yours looks like it almost goes straight up and down at
Yeah, I know.
like some threshold.
Yeah.
Like you have some physical interpretation of what, like is that a 1 or is that a?
Not really. So here for a while is not really 1. No, you can draw any interpretation heuristically. The idea is that after some point, the links are far away from each other, such that they don't really interfere each other using the Waterfilling. And I don't really have any nice explanation. No.
Suppose you did some other physical model, like all the desired transmitting pairs are distance d apart, right? And then you throw down these links, which are always at a fixed distance in some big box, right? So that is, as long as the density of the links isn't too high, there's sort of a high probability the other links are far away, right?
Yeah.
So
that would be.
the question is, if you sort of did all these, so you have some other, the box size would be your geometry constant, like the way d is. Somehow, do you think you would maybe get the same kinds of results in terms of some kind of an SI in R or some kind of a, is this somehow, when you look at these curves, are they really dependent on the sort of the structure of your own geometry that you created?
Yeah. I don't know if this will look like a steep step or not, but of course each condition is more relaxed than the previous one, so whatever the new, it will always be like, maybe a little different. One more thing is that, our condition is improved, but our condition also works for the simultaneous. That's like the main contribution.
So one more thing is that, so you have this theorem that says, okay, so under these fairly easy to satisfy conditions, this algorithm converges, right? Is it always guaranteed when the condition is satisfied to converge to the same thing? I mean, is your theorem that, when this condition is satisfied, you always
implicitly because the conditions also imply uniqueness of the Nash equilibrium. Okay. It does. That's a good question. Well, this is an illustration of your previous point. Actually, comparison of the convergence of the sequential versus simultaneous. So, in the sequential, the user is waiting all the time until it's his time to be updated. This is 15. So, convergence is slow inherently because it's waiting all the time. This is one user, this is another user, and this is another one. So, in the simultaneous, in 2 iterations, everything has converged already. This is blue is simultaneous, and the red, the difference is huge. Oh, and we have analytical results that show that you improve the convergence with a factor of q, the exponent. So the convergence is exponential, and the exponent is q times larger. Actually, let me say something. Well,
so it scales with the number of links.
Huh?
Really? So you converge even faster the more the links? Is that what you're saying? You said it scales with q, right? Q is the number of links.
Yeah, but then you have a constant factor outside that also changes. So this is only to compare both. But do you want to hear a few words about the proof? It's only 1 minute. The idea is that you need to prove at the end that the update that you do with the waterfilling operator is a contraction mapping. Okay? This is what you need to do. And, well, these are the key elements that we used at the end. Okay? After a long, long time, at the end, we isolated the 3 key elements that are important. One is the possibility to write the waterfilling as a projection. Okay, we saw that before. The good thing about this is that there is no water level here, so we can use this later. Okay, the second key result is this non-expansive property of the projection, which is a nice result to remember. Maybe you will be able to use it sometime. It's really simple, right? So the difference between 2 vectors decreases if you project both onto a set. It has to be convex, though. Okay, but we didn't know this before, okay? So essentially, we implicitly proved this, and then we realized that we were doing this, and then we found, it looked very clearly, it looked like some well-known result, and then, yes, we found the result. So this is well-known. And then, this is the last part. So at the end, you want to prove that the waterfilling operator is a contraction mapping. And if you look, this is like a combination of these 2 things. You combine this with the waterfilling operator. Why? Because now the waterfilling is a projection, so you can use it here. This is a projection. So now you can put here the waterfilling because it's a projection. That's the nice part. And then if you do that, you get this, and then you get this magical alpha. If alpha is less than 1, this is a contraction mapping. The Nash equilibrium is unique. So the only thing you need to do is to find the conditions under which alpha is less than 1. Precisely the conditions under which alpha is less than 1, this looks similar, right? So these are the conditions. Okay. Give me a few more minutes, because actually I want to say a few words.
What do you mean by block?
Oh, yeah, well, this is...
L1 norm?
Yeah, no, this is not the Euclidean norm. So here, this waterfilling doesn't have an index as opposed to this one. So here I am stacking all the waterfillings, and this norm is taking the maximum of the norms of each block. So when proving this, you need to play a lot about different norms. So you cannot just use any norm. Oh, I use the Euclidean. No, you have to play around. You have to choose the right norm such that you can do whatever you want to do. Really, it's not easy. Once you know the norm, you can easily verify everything. But to choose the norm, this is difficult. So yeah, this is the norm that you have to use. Okay, let me summarize these simultaneous. Okay, nice property.
So isn't this waterfilling operator just like a standard interference function?
I don't think so.
What do you say?
He has no monotonicity or anything. He's doing, I mean, it's what he says he's doing. He's doing a contraction mapping with a specially chosen norm, and his key thing is that somehow the projection is not
Yeah.
injuring his contraction.
Yeah, you cannot use standard functions for this. Anyway, so this still.
The key thing is the projection remains back in the space and it actually converges to it.
This looks nice, the simultaneous waterfilling, but still there is a drawback. Simultaneous still requires some synchronism, right? All of them have to be updated at the same time. That's not good in practice. Can we improve that? Yes, we do. We can. We can use an asynchronous. Okay? Synchronous, totally asynchronous, meaning that each user updates himself at any time with any frequency, and also each user may even use an outdated measure of the interference from the other ones. Okay, so it's completely realistic. If we can prove convergence for such an algorithm, then this is like a unified framework for all the algorithms. Clearly, the 2 previous algorithms are just a particular case of this. Right? Well, this would be the description of the asynchronous. It's like before, but this is more general. So user Q is updated only when the time belongs to this set, TQ. In fact, TQ denotes the set of times at which user Q is updated. So we can choose any kind of scheduling or whatever. Okay? So otherwise, it's not updated. when it's updated with the Waterfilling, but maybe using outdated information. This tau RQ denotes the most recent time at which the interference from R is estimated by Q. So if this is equal to n, it means that it's the most recent, right? If this is equal to n, it means that it's using the power from the previous iteration. But it could be less than n. Okay? So it's very general. Well, we can prove convergence of this also. This is the main result, but look at this one. Does it look familiar? It's the same result. The same conditions guarantee convergence of the asynchronous. Okay? To prove convergence of the asynchronous, you need to use more machinery.
You usually need some kind of a box condition.
Yeah, all these.
For going into smaller and smaller boxes.
Yeah, exactly. All these Bersecas, totally asynchronous setup. Exactly. Yeah. So now let's see how the two previous algorithms are just one particular case of the asynchronous. The sequential, what it does is it updates every q iterations. So the times at which the user is updated is, well, some offset and plus q plus 2q. That's it. And then there is no outdated information, so tau is n. Right? Now, simultaneous, well, each user updates every iteration. And there is no updated information. But now you can play around. You can say, okay, I want to use the simultaneous, but with outdated information. You can generate new algorithms, and they all will converge with the same condition. Well, I will skip that, but this is, in a real life, you have synchronization errors. Time offsets, frequency offsets, right? Maybe the oscillators of the different users may not be synchronized. You may have delays that destroy the orthogonality of the carriers. Then what happens? If so far we have been assuming orthogonality of carriers. What if they are not orthogonal? Everything still will work fine. That's the point. And we have these conditions for convergence and their offsets. Okay, so
going back even the previous case, so every time the users have to estimate this interference, right? For every step of doing the
yeah.
That's true.
Anyway, let me summarize. We started with an introduction to Waterfilling solutions from a single user perspective. We saw the classical Waterfilling. Then we saw many different Waterfillings in different areas, in signal processing in different areas. And then we gave a more general graphical interpretation in 3 dimensions of the Waterfilling. Then we saw this new geometric interpretation of the Waterfilling as a projection. That was the key point to prove convergence later. Then we talked briefly about the role of Waterfilling in the multi-user multiplexer channel. We talked briefly about the role of Waterfillings in the multi-user broadcast channel. And then this is the second part of the talk. We talk about the role of Waterfilling in the interference channel. We saw the sequential and simultaneous Waterfillings, and we gave conditions for convergence. And then we saw the asynchronous, which is like a unified framework of algorithms, and we gave the conditions. So thank you for listening to me, and if you have any question.